We're going to take a look at exponential functions and specifically the characteristics of the exponential functions. Now, exponential functions and the family of exponential functions really have wide-reaching implications, specifically in natural sciences and even in finance. Let's get started here. Suppose April is sick and goes into work. On the first day, she infects 2 people. On the second day, those 2 people infect 2 more people. If this pattern continues, how many people are infected on day 5? So, day 0 indicates generally 1 person. After 1 day, this 1 person affects 2 people. On day 2, the 2 people infect 2 people each, which means they infect 4. Now on day 3, the 4 previous people each infect 2 people, 8. And this pattern continues until day 5. So let us graph this on the axis. So I'm just going to mark this up 1, 2, 3, 4, 5, 6, 7, 8 very quickly. This will be my t-axis, my time, if you want, or x, my x-axis. This will be my y-axis. And as the day is 0, we have 1 person infected. If the day is 1, we have 2 people. On the second day, we have 4. On the third day, we have 8. And then all of a sudden, my graph runs out of space. But this is what an exponential graph looks like. It is a curve. And it's not quite a parabola, but it definitely has that curving element to it, especially for exponential growth. So let's move on. Let x represent the day number, and y represent the number of newly infected people, so x and y, like we did for the graph. Construct an equation for the above situation. So the above situation, example of an exponential function whose basic exponential function has the form y is equal to cx. And our exponential function is going to be y is equal to 2 to the power of x. So we are going to consider 2 cases of exponential functions. Now here, c, normally we call c our base. By the way, our base for the previous example was 2. Always our base is going to be positive. However, we're going to deal with 2 special cases. One where c is greater than 1. And the second case is where c is between 0 and 1. What we have when c is greater than 1, exactly what our previous example was, is that the function will have the following character, will look the following way. It'll have characteristics like we have an asymptote here at y is equal to 0. We have a y-intercept of at 1. And it really comes from the form y is equal to cx, and maybe let's just put a value for c, 2. As x gets larger, so does your y. Unless, no, that's absolutely true. As x gets larger, so does y. Now think of it in the other way. As x gets smaller here or more negative, the y values diminish. However, if I ask a question y is equal to 2 to the power of x. Can you think of any x value in which y would be negative? No, there's no exponent that is possible to make y negative. All right, so this is case 1. The domain of this function is going to be negative infinity to infinity, right? There's nothing restricting the value of x. My range is going to be 0 to infinity. Now, if you notice, both are round brackets. This function, the y value, can never be equal to 0. My x-intercept, well, what is my x-intercept in case 1? Well, if we notice, there is none. My y-intercept is 1, and I have this asymptote, and there's only one asymptote, and it's a horizontal asymptote. And that horizontal asymptote is y is equal to 0. And recall from a definition from an asymptote, as x, in this case, as x goes towards negative infinity, the value of our graph, f of x, will approach 0. That is, as x gets more and more negative, the y values get closer and closer to 0. Now, let's look at case 2. I'm going to take a sample example, like let's c equal to 1/2, say. So what we know is as your exponent gets larger, the value of y will actually get smaller. Again, we'll have a y-intercept of 1, and we'll see why that is, right? Let x is equal to 0. 1/2 to the power 0 is 1. But this graph looks something like this. And I'm just going to draw the asymptote. Again, we have an asymptote at y is equal to 0 here. And by the definition of my asymptote, as in this case, as x gets infinitely large, my y value, or the value of my function, gets close to 0. As x gets more negative, my y value actually gets more positive. So, by the way, that's a nice round bracket. My domain is negative infinity to positive infinity. Again, my range goes from 0 to positive infinity. My x-intercept, again, there is none, but my y-intercept is 1. And this is going to be an important attribute, my y-intercept. So anyways, I showed you 2 different cases. Let's go on to a more specific example.